This is something called the Drude model, which is kind of basically what we said. We're saying it's a positively charged atomic cores, mobile electrons superimposed on top of these atomic cores, and we're just dealing with it as in the sort of classical way and not involving any quantum mechanics. Okay, so that's called the Drude model. So in the Drude model, you have these mobile electrons. And let's say you were able to somehow apply an electric field in here. So here's our conductor. And let's say there's some positive charge over here. And that is going to produce some electric field, applied electric field in that direction. And we're looking at the mobile electrons inside. Let's just focus on a single electron, okay? Electron is completely free to move around, and now there's an electric field in that direction, right? So what's going to cause what? There's going to be a force on the electron that way, right? From F equals QE. Well, if there's a force on a mobile charge, or force on any object, what does that cause? Acceleration, right? So the electron would speed up. If we were to plot the speed of an electron in this applied electric field versus time, it would look something like this. So the electron starts, let's say, at rest. It increases in speed due to the applied force, the applied electric field. But every so often, a mobile electron is going to collide with one of these positively charged interatomic cores. Okay? Collides with a core and basically loses all of its momentum, loses all of its speed, gives up its kinetic energy to the atomic core, and so the electron speed drops down to 0. Well, there's still this force here due to the applied electric field, and so the speed increases again, but maybe now it collides with the core here, drops down to 0. Speed increases again, maybe goes on for a little while, collides with the core, drops down to 0. And this keeps going over and over, and you get this sort of sawtooth-looking graph. If I were to average all this out, we'd find some average speed for the mobile electron. And this average speed I'm going to call V bar, V with a little bar over it. This is called the average speed or the drift speed. Okay. So on average, the electron moves on a roughly average constant speed with an applied electric field because of this sort of frictional force where it's constantly colliding with the atomic cores and slowing down and speeding up and colliding and slowing down. So that relationship, that behavior is parameterized with an equation which says that the drift speed of mobile charges inside a metal is equal to U times the electric field. What is U? U is called the mobility. Okay, and its units are just meters per second over newtons per coulomb. There's no special unit for it. It's just giving the mobility of the charges, how easily they can move, how fast they will move, given a particular applied electric field. Okay, so given this, there's a special case when the average speed is equal to 0, when the electrons overall net are not moving. We call this situation static equilibrium. So static equilibrium, charges aren't moving. Well, let's look at what's possible and what isn't when we have a situation of static equilibrium. Here's V. Let's make a little table. V and the net electric field inside the material. Let's say V is not equal to 0, E not equal to 0. Is that possible? Sure. But is it a case of static equilibrium? No, this is not static equilibrium. V not equal to 0 and E equal to 0. Is that possible? This equation says it can't be, so not possible. V equal to 0 and electric field not equal to 0. Is that possible? Nope. So there's only one possibility left when we're in static equilibrium. That is, if we're in static equilibrium, if the drift speed of these mobile electrons is equal to 0, the net electric field has to be equal to 0. So this is the only possibility in static equilibrium. And you say, wait a minute. How can that be possible? Because let's say we have this situation. Here's a neutral block of metal. I bring a positive charge near this neutral block of metal, and now this positive charge is applying an electric field. So I'll call this, I'll call this charge 1 just to distinguish. And so this is E1 due to charge 1. Okay? What's going to happen to the mobile charges in here? They're going to shift, right? And so the negative charges, the negative electrons in the electron C would shift in what direction? That way. So I'm going to end up drawing electrons over here, positive charges over here. But now I have a separation of charge. What do those charges create inside that material? Okay, it's a dipole, creates a dipole. So the charges, just think about superposition, right? Here's the electric field due to this charge, but now we have electric fields contributed by the charges on these surfaces, right? So let me think about the right side and the left side. At the same observation location, what's the electric field due to the charges on that left side? What's the direction? That way, yeah. What's the electric field due to the charges on the right side? Same direction. When I add it all up, what's happened to the electric field? The net electric field has, well, not just, okay, well, it's changed. Has it changed direction? Well, maybe not yet, right? If I add this, if this is, say, fairly large, and I add these two together, then if I add these two vectors in the opposite direction, I've changed the size, right? So the net electric field's gone down. We still have some net electric field, so charges will continue to move because of V equals UE, and so the charge builds up even more on one side and on the other. And if the charges increase here, then these electric field sizes increase. And when does it all stop? When it's equal to 0, when the net electric field is equal to 0. Okay? So there's some, when you bring a charge nearby, there's some short amount of time when things aren't in static equilibrium. The charges are moving about, okay, and things are shifting. When does it stop? When does that shifting stop? When the electric field is equal to 0. So this is an important result. The net electric field inside a conductor at static equilibrium is 0. And it's one of those sentences where every single word is absolutely important. It's not just the electric field due to a single object, it's the net electric field due to everything. Not in an insulator, it's in a conductor. We're talking about static equilibrium, not cases like in a circuit where we'll see later on where there are charges moving continuously. We're talking about a static equilibrium situation, so V is equal to 0. V bar, I should say, is equal to 0. And the net electric field is equal to 0. Okay? So that encapsulates a lot, but it's extremely important to understand. Okay?